All right. Well, I'll get going with the introduction. I'm delighted to be here for our last SGP event of 2022, our last proxy primer of the year on carbon isotope chemostratigraphy, something that's of interest to a lot of us. For those of you who aren't familiar with SGP, I think most people here are. We are an open geochemical research consortium trying to understand trends in paleoenvironmental evolution across Earth history. If you're not familiar with SGP, I'd encourage you to check out our website and get involved. We'd love to have everyone involved. We started this proxy primer series as a way to accessibly explain the basics of a geochemical proxy or method to a broad audience, and also to create a curated lecture series on our YouTube channel, such that people can go back for teaching purposes or just to understand a proxy when they come across it and want to understand it. And then finally, to provide an open space for interaction with experts on each proxy. And so today we're delighted to have Dr. Selva Marroquin, who is going to tell us about carbon isotope chemostratigraphy. Dr. Marroquin did her undergraduate at Tufts before moving on to a master's degree at University of Texas in Austin, which was a little bit more paleontologically based. She then went to Virginia Tech to do a PhD with Ben Gill that was much more geochemical. And so she has kind of this background in both paleontology and geochemistry, which is great for understanding things like mass extinctions, which are, of course, the interaction of life and the environment. She's now a postdoc at Caltech working with Alex Sessions. She has expertise not only in the carbon cycle, but also in sulfur cycle and iron-based proxies. And sorry, we have maybe one person that is not muted. If people could mute themselves when they join, that'd be wonderful. Yep. And sorry, she is now moving on to an assistant professor position at University of Wisconsin-Madison in about a year or so. And we're delighted to delighted to have her here. So I'll stop sharing, and if you would like to share your screen.
Yeah, thank you, Eric, for the introduction. And let me just get into Zoom world and share my screen. Okay, ideally, you can all see this, okay? And then, of course, if anything's not working with moving the slides forward, just let me know and I'll change some things. I changed just one thing about the view. And then I'll get going. Okay, so thank you, Eric, for the introduction, and thank you all for being here. I know it's kind of a busy time in the semester, as well as just the World Cup going on and everything in the world. So as Eric said, I have kind of expertise across different subdisciplines, and that kind of colors my view of carbon isotope chemostratigraphy and carbon isotopes in general. And so for today, I'm going to be giving a pretty broad overview of the system and considerations when looking at carbon isotopes in deep time, and kind of some maybe ways forward to be responsible about interpreting these moving forward. And I like to start my talks by giving a bit of a background, and Eric did a nice job of introducing me, so I don't have to spend too much time on that, but it's just to allow you to see some of the perspective of where I'm coming from when I talk about deep time. So first and foremost, I consider myself a geologist. Most of my degrees are in geology, and a large component of my research involves field geology and excavations. As Eric said, I have a master's in paleontology and exceptional preservation of squid, of all things, in the early Jurassic. My PhD focused on sedimentary geochemistry and biogeochemistry, looking at redox dynamics in deep time and iron, sulfur, and carbon cycling. And some of the tools that I used were stable isotope geochemistry, like carbon isotopes and sulfur isotopes. And this all kind of comes together with my expertise or my interest, which is understanding paleoceanography. So understanding deep time climate change and how that affected our oceans and marine biota, linking extinction with mechanism and chemistry change. And the approach that I take to try and ask these questions is referred to as kind of an Earth systems approach. That if you want to understand what's happening in the oceans and the Earth system, you have to have a sense for what's happening in the atmosphere, the hydrosphere, the lithosphere, and the biosphere. And all of these things really intimately work together and lead to kind of a cohesive understanding of the system as a whole and how it's going to respond to CO2 changes or to biotic changes that will inherently affect CO2. And so for today, kind of the big question that I'm trying to tackle or introduce here is what can we actually learn from investigating carbon cycling across Earth's geological record of climatic and environmental perturbations. And in order to get into the geological record, I like to start with a bit of significance for the modern, where we are today, and why understanding the past is really important. So as we all know, one of the main issues facing our climate today is the rapid introduction of CO2 into the atmosphere due to anthropogenic forcing and burning of fossil fuels. And that's already having a pretty significant impact on our Earth system, and specifically the oceans, which are going to be the focus for the most part for the talk today. But we're already seeing warming ocean conditions. We're seeing ocean acidification leading to coral reefs dying, and also loss of oxygen in the water column, leading to dead zones in the oceans in different areas. And so there's already feedbacks being expressed in our oceans today as a result of modern carbon dioxide emissions. And if we look at a box model of modern carbon cycling, this is a pretty involved diagram, and I'm not going to get into all the details right now, but this is just meant to show this is a really dynamic system, and you have a lot of inputs and output into the ocean system in the modern that we see. And here, this is showing is different sources of CO2 or methane and their isotopic composition, and then the kind of the archives that we have tracking these isotopic compositions in the rock record. And one of the big things that's important to note here is the production of organic material. And this is what I often focus on for most of my talks in deep time, just because most of my work focuses on source rock material and the production of organic matter and the fractionation associated with that. But for this talk, I want to focus on that as well as carbonates. But this is really important to introduce at this point. What this is showing is just a very basic chemical equation of the process of photosynthesis, where if you push this reaction in this direction, this process of forming organic material consumes carbon dioxide and produces oxygen. And in the modern ocean, 99.5% of organic material gets respired, meaning it just gets recycled. It gets produced and then oxygen reacts with it and it gets re-respired in surface oceans. If you change redox conditions, however, you can change the amount of organic carbon you bury. So this is intimately linked with biological processes as well as chemical changes in the ocean system that affects how we bury organic carbon or carbonates, for example. And so why is this important? Is because in deep time, it's one way to remove CO2 from the atmosphere. It's kind of this natural CO2 sequestration in deep time with these feedbacks in the Earth system. So the burial of organic matter and carbonate influence atmospheric CO2 and oxygen on really long timescales, on geologic timescales. And this knowledge has been used to leverage reconstructing CO2 and oxygen in deep time. And this has implications for the isotopic composition of carbon through time as well. You can see here between carbonates and marine organic matter, there's clearly a different isotopic composition for organic material than there is for carbonates. And this is because there's a fractionation associated with production of organic material, where photosynthesis and producing organic material has a preference for the lighter isotope, resulting in a more depleted signature here. But when we look in the rock record, we don't have all of these details. We don't have a proxy for primary producers in the surface oceans. What we do have are two main archives of organic production and calcium carbonate production. And that's via the burial of organic carbon in predominantly shales, but also sometimes in carbonate systems, and calcium carbonate in platforms or different environments. So these are the two archives that we need to use in deep time to just reconstruct inputs and outputs to the system and changes through time to reconstruct atmospheric CO2 and oxygen. And another reason why this is really important, and I want to bring in some of the biological aspects here, is if we look at this Sikorsky curve of Phanerozoic marine families, so diversity through time, the 5 main mass extinction events are pointed out here. And these have all been associated with changes in carbon isotopes as well, in one direction or another. So clearly there's a link between extinctions and biotic changes, as well as carbon cycle changes and directionality of isotopes through time. So there's links here that are really important in the rock record and can be used to tell us something about where we might be going in the future. So to bring it back out to the modern perspective, this is a really good review paper from 2020 addressing why we need to be investigating past instances of climate change to understand our Earth system moving forward, given that we're kind of venturing into unprecedented territory of CO2 emissions at this time. But we can use the rock record and carbon cycling in the past to kind of assess the plasticity of the Earth system and how far we can push it before certain feedbacks start kicking in. And so to me, that's the most important aspect of understanding carbon cycling in deep time, is assessing these feedbacks. So this is just kind of a summary of that and the significance for why this is important. So you can look at case studies for rapid warming, extinction, and carbon cycle perturbations in deep time to say something about where we might be going in the future. The outline for the talk today, first I want to talk about carbon isotopes as a proxy and how to apply them. So just the evolution of the measurement, as well as the different pools that you're trying to track by looking at carbon isotopes and different materials that you can use for analysis. And then the second part of the talk, I want to talk about considerations and kind of caveats with using carbon isotopes from carbonates versus organic material, as well as ending on talking a bit about chemostratigraphy, correlation, and some of the best practices when doing that. I was hoping to have time to talk about some TJ boundary things because that's near and dear to my heart, but I think for the sake of time and to leave more time for discussion, I'm leaving that out. So I'll just be talking through the proxy and then what you need to consider when utilizing these different things. So this recent paper from and Husson does a really nice job of reconstructing kind of the evolution of carbon isotopes through time and just carbon in general, starting from the late 1920s into the modern. And this is just addressing when mass 13 of carbon was discovered, how it was related to C12 in order to say something about organic versus carbonate burial and the fractionation associated with them. And I want to pause here in 1953 because this is when we start to get into putting these values onto a standardized scale. And this is per mil notation and PDB, which refers to PD belemnite. And so this is a good opportunity for me to introduce the concept of delta notation. And I've already been showing delta notation throughout, but I want to actually tell you what that means and how to interpret that moving forward. So delta notation for carbon is looking at the ratio of two different isotopes within your sample relative to a standard. So for carbon stable isotopes, this is referring to C12 versus C13, so the lighter or heavier isotope. And then this is showing the abundance of these two in the modern. And when we look at delta notation, what we're actually looking at is the absolute ratio of the rarer isotope to the more common isotope in your sample relative to a standard and putting it on a per mil notation, just so it's numbers that we can deal with. If we put it on percent, they'd be pretty small. And this is that Vienna PD belemnite that's used as a standard to compare all of our samples to. So going back to this evolution of carbon isotopes, in the 60s and 70s is when the long-term carbon isotope trend through the Phanerozoic was reconstructed. And then in the 70s is when people started using the carbon isotope trends through time to reconstruct box models and kind of simple box models of inputs and outputs of reconstructing carbon isotopes in the Earth system based on the fraction of carbon leaving as organic material versus carbonate, and using box models to reconstruct that. And so here on the right is just the carbon isotope trend in carbonate carbon. So you can see it's basically in 8 per mil space here. And there are some clear shifts at certain time intervals, but overall stays within that 8 per mil window for the Phanerozoic. And then over here on the left, what I'm showing is carbon isotopes carbon isotopes associated with different archives of carbon in the modern system. And these boxes are reflecting the size of the given archive, and then the fluxes between them are these arrows. And so this knowledge was used to reconstruct atmospheric CO2 and oxygen in deep time. And here what I've circled are the reservoirs or the archives of carbonate versus organic carbon. And so the size of the reservoirs are very different. And another thing to note here is it's commonly assumed or thought that carbonate sedimentary rocks are reflecting oceanographic dissolved inorganic carbon, so it doesn't have as much of a fractionation associated with it. It's close to our standard, which is at PD belemnite, whereas organic carbon production carries with it a very significant fractionation that can vary, but this is showing an average about -23. Meaning that when organic matter is being produced, it preferentially incorporates the lighter isotope, resulting in a more depleted signature. And so this knowledge is really important for actually reconstructing some of the early models of CO2 and oxygen. And then pushing this forward through to the 80s, as things developed and moved forward, in the 1980s, you started to get the ocean drilling project, which cored marine sediments, and this is where you started identifying oceanic anoxic event intervals and organic rich shales, and using carbon isotopes as a correlative tool to compare disparate sites and use it as a time constraint. And this is really interesting. A follow-up in that paper, the next figure just shows that after the 80s, the prevalence of carbon isotope stratigraphy in papers just kind of took off and has become more and more popular and more used with time. So this is a good time to start talking about it and kind of the idea for consensus of what we think is good or best practice moving forward. Okay, so now that I've introduced kind of the spread of evolution of measuring carbon isotopes, now I want to introduce how we track different processes using carbon isotopes. So here on the left, what I'm showing is carbon isotope space from -60 to 20 and different materials or archives that have specific isotope signatures. And so here on the right, I'm showing a really simple schematic of carbon isotopes through time, whether it's negative or positive, where oldest is at the bottom and youngest is at the top, and some of the processes that may push you in the negative or positive direction. And this is a very simplistic version. This is not meant to address all the nuance in these records, just to show overall very simple ways you could push things in the negative or positive direction in carbon isotope space. So first, for the negative direction, a very simple kind of forcing for that would be to introduce isotopically light carbon in the form of methane or in volcanic CO2, and that would potentially change your atmospheric carbon dioxide and therefore your dissolved inorganic carbon isotopes. And then in the positive direction, two potential things you could change here would be your inputs. If you weather more carbonates and bring in more carbonates, you could potentially push in the positive direction. And if you change the burial of organic matter. So if you change your output to bury more organic material and remove more of that lighter isotope, you can leave the residual pool enriched in the heavier isotope. Over time, that could lead to a positive excursion. So this is kind of just overview, big picture, not taking into the nuance of all the different things that need to be considered when looking at these different archives. But one really nice thing is we can see this happening in the modern. So this is referred to as the Seuss effect, which is showing that the change in atmospheric CO2, so here in black is atmospheric CO2 through time, and you can see the increase here with anthropogenic forcings and the carbon isotope composition of CO2 with time as well. And as we've increased CO2 by burning fossil fuels, you can see a decrease in the isotopic composition of carbon isotopes, reflecting that C12 being re-released into the atmosphere. This is a nice real world example of seeing that link today. So there's a lot of different materials that can be used for carbon isotope measurements, and they're different applications. So I've already introduced the concept of carbonate and bulk organic carbon contents, but there's also wood and paleosol organic carbon, paleosol carbonates that can be used to reconstruct atmospheric CO2, so nodules within paleosols, and then different biological materials that can be used to reconstruct diet in deep time. And then these are more useful on the more recent time frame when we have ice cores where you can actually sample atmospheric CO2 and carbon isotopes and stomatal index of leaves to see atmospheric CO2 concentrations. And these all have different time scales for their archives. And so you can see here the time scale for a given archive and then what it spans. So for today, I'm going to be focusing, like I mentioned, on marine sedimentary records. There are terrestrial, like lacustrine records that could be talked about as well, but for the sake of simplicity, I'm leaving it with just marine records for today. And so this is what I'm going to be addressing and talking about for the rest of the talk is carbonate minerals versus bulk organic carbon. And carbonate minerals should theoretically be reflecting dissolved inorganic carbon in the oceans, whereas bulk organic carbon is reflecting the isotopic composition of biomass. But there's nuance to these and there's more details than just that, but simplistically, that's what it's supposed to be recording. Okay, so now that I'm through the introduction of these, I want to now get through how do you measure carbonate, organic, and organic carbon isotopes, and how do you interpret those records and get around some of the caveats within each of these different archives. And then finally into the chemostratigraphic correlation. So this is going to take up the bulk of the rest of this talk. Okay, so some considerations for utilizing carbon isotopes in carbonate versus organic matter. Both of these are susceptible to isotopic heterogeneity in whatever the reservoir is. For carbonates, you have to consider non-equilibrium isotope compositions. These are referred to as vital effects, which I'll get into in a minute. And for both of these systems, you have to consider alteration from the original isotope composition in the form of diagenesis, which looks different for carbonates than it does for organic matters, different considerations that have to be taken. And then ultimately, in order to use these for chemostratigraphy, you have to be able to separate local versus global signals that are kind of imprinted in the record for not only carbonates, but also organic matter. So organic matter is inherently a local signal, but can be used if you have enough records from different areas and you can kind of separate out local versus global signals. You can try to use it to say something about global carbon change. And then carbonates, on the other hand, are sort of thought to be more of a global signal. However, they're susceptible to local changes as well in the form of diagenesis and then vital effects, as I mentioned. Okay, sample collection. So I'm not going to spend too much time talking about sample collection and analytical measurements, just because carbon isotopes on the spectrum of geochemical analyses are pretty straightforward relative to other geochemical processes and proxies. But just generally what needs to be done is either you go to the field and log a section for context so that you have a stratigraphic context and you take about fist-sized hand samples, or you can go to a core repository and look at cores and describe the lithologies and drill samples where permitted. And here what I'm showing in the middle is when you have those samples, if you have hand samples, bringing those samples back to the lab, cutting off any weathered surface and exposing a clean face so that you can powder fresh fabrics. Here, these are billets for thin sections that it's nice to have the thin sections so you can have the petrographic fabric in association with your carbon isotopes as well. Okay, so ultimately I'm going to be describing measuring carbonates versus organic carbon from a given sample using a mass spectrometer, an isotope ratio mass spectrometer. And so the actual instrument doesn't change, but the front end or the peripheral is what they're called will change when you're measuring carbonates versus organic material. So if we imagine that the sample is a mixture of carbonate and organic material, in order to analyze your carbonate fraction only, what happens is you put your sample into a vial that's sealed. You purge your headspace with helium to remove any atmospheric CO2 that may be in the headspace. Then you add phosphoric acid into the vial to dissolve your sample and release your carbonate as CO2 into the headspace of your vial. And you allow that to react fully and equilibrate. And then you can run it on the gas bench and analyze the CO2 from the headspace on your mass spectrometer. So that allows you to get only the carbonate fraction and not the organic fraction. Now, if you want to measure the organic fraction, what you need to do is take your sample and remove the carbonate fraction to leave behind only the organics. So here, Kayla, who's was an undergraduate at Virginia Tech and now a master's student at Virginia Tech, offered me this picture, which is really nice. I appreciate that, of her in the lab actually decarbonating a sample. So bulk powder, measure out the sample, weigh the sample, and add dilute acid to remove the carbonate fraction and leave behind only the organic material. So once you've removed all of the carbonate, then you can rinse your sample and dry your sample, weigh your sample to make sure you know how much was lost when you decarbonated it. Weigh it into a tin, seal the tin, and put this on an auto sampler, an elemental analyzer. And so this is different than the gas bench headspace analyzer. And what it does is it takes your sample and combusts it at high temperatures to convert it to CO2, and then collects that on a GC column that then goes into the mass spectrometer to allow you to get isotope ratios. In my experience, the way that I've done this, typically you run multiple times. And the first time, unless you know the amount of organic carbon in your samples before you weigh them, typically the first step would be screening your samples. If you just had an EA, it would be nice to just know the amount of carbon in your samples. But if you don't have that, running them for carbon contents first and then re-weighing your samples so that you're introducing a similar amount of carbon for each of your samples is really important when you're correcting for carbon isotopes. And that's because you can have instrument effects and linearity effects based on the amount of carbon being introduced into the machine. If it's very different from one sample to another, that can affect your isotope ratios. Okay, so coming back to carbonate versus organic matter, I want to start by talking about the inorganic record and how we account for some of these caveats associated with it and what it's actually recording. So for carbonate records, what this is showing is modern carbon cycling in the oceans, as well as the biological pumps. So this is showing a profile of DIC with depth and carbon isotopes with depth. And this profile here of more enriched surface waters versus more depleted deep waters is reflective of this biological pump. And so here on the left, this is showing that in surface waters today and in the past when we had active surface waters and recycling, organic matter is produced and very quickly re-respired. But some of that organic matter that's enriched in that C12 can go and get exported into the deep water. And when you do that, you preferentially remove C12 from your surface waters, leaving it slightly enriched relative to deeper waters where you have respired organic matter that leads to a slightly more negative deep water signal. And this is important because if you have carbonates being precipitated from more shallow surface waters versus deeper waters, that's going to be recording two different DIC signals. And carbonate minerals precipitate in different ways as well. So I mentioned vital effects, but this is a good overview of different organisms and then their isotopic composition relative to 0 here is meant to indicate seawater, what DIC theoretically is. And so abiotic carbonates or biogenic carbonates that precipitate pretty slowly typically have carbon isotope compositions that are near equilibrium with DIC, meaning that they're representing the oceanographic condition. However, there's many biogenic carbonates that precipitate out of equilibrium with respect to their carbon isotope compositions. So this is vital effect. So here you can see a spread of different isotopic compositions for different organisms. And this, there's competing models for what vital effects are caused by, but likely it's a combination of metabolic processes where certain organisms prefer different isotopes over others, and then kinetic isotope effects where it might be easier to use the lighter isotope over the heavier isotope, depending on the precipitation pathway. And this is very simplified of a pretty complex problem, but it's meant to show, this cross plot is meant to show that these different groups of organisms cluster in different areas based on their vital effects. And this cross plot of carbonate carbon versus oxygen isotopes is really important, and will come into play in a moment here when we start to talk about diagenesis and original signals of carbonates. One way to get around this and these vital effects would be to choose carbonate minerals that are from organisms that are known to precipitate calcite in equilibrium with water. So this plot is showing a cross plot of different organisms or cements that cluster together in similar space, but are kind of disparate along this line. And also to generate records from a single taxon or group of taxa where the fractionation is relatively consistent. So if you stick with one taxon, then you can kind of mitigate some of these vital effects. And so I mentioned this cross plot of carbon and oxygen as a way to track alteration of carbonate. And this is because as you have a carbonate rock that's formed at Earth's surface, it can be very reactive to meteoric waters. So as you have meteoric waters coming through, you can alter the oxygen isotope signal and the original carbonate carbon isotope signal. So here what this is showing is that your water to rock ratio affects your oxygen isotopes first. So you may not affect your carbon isotopes initially, but with time and with enough water coming through, you can slowly start to affect your carbon isotopes as well. And so this kind of classic J curve is what's used to imply alteration of original marine values. And there's ways around this. The first way would be to screen your samples and use archives that have a higher preservation potential. And so here, this kind of screening tool from Marshall from the early 90s is addressing different organisms or cements that are ideal for preserving original signals versus those that would be potentially reset. And then here's another really helpful kind of flow chart for selecting carbonate samples and assessing diagenesis at different scales. And so this alteration of oxygen and carbon isotopes can be indicated by alteration of the original textures, original mineralogy, or other geochemical parameters, and also changes in the optical properties. And so this really, what this means is it's really helpful to have thin sections in petrography to support your isotope values or to interpret them moving forward. Okay, so moving into organic matter and kind of the caveats of that system. I mentioned isotopic heterogeneity, and so now I'm going to talk about diagenesis in regards to organic material. So one of the big things to consider here is that I mentioned that organic matter in the modern is about 99% of it gets respired. So here on the left, this is an overview paper from Kate Freeman from 2008, showing plankton, so original organic material, and then as that composition changes with depth and into the sediments. So you can see here in the surface waters, the majority of the organic material that's produced is pretty labile. So it's really reactive. A lot of organisms want to use it. It's easily recycled. And these are amino acids, and those get consumed very quickly. And as you go down in depth, you kind of are left with this more refractory or recalcitrant organic matter that's less, I don't like using this word, but a lot of people use it. It's less juicy. It's less ideal for microbes to use in their microbial processing. So as you go down and through early diagenesis, you end up with a higher proportion of your organic material that's this recalcitrant or uncharacterizable organic material. And so most sediments in deep time are uncharacterizable. And then we have lipids that we can use as a different tool. And another thing to consider is late diagenesis and specifically thermal alteration. So as you bury organic material, you can heat it and drive off some of the lighter isotope, C12. But this study from the early 80s showed that even when you do that, the effect is relatively small. So typically less than 1 per mil in this specific hydrous pyrolysis experiment. And now I want to talk a little bit about a kind of a real world example of trying to assess local versus global conditions by talking about the Torshan oceanic anoxic event, which is one of kind of my favorite events in deep time, but also highly studied. It's very unique because it's significant for having a very strong negative carbon isotope excursion associated with a certain biozone that's well calibrated in the early Jurassic and thought to be associated with lip volcanism. But this study from the early 2000s did a nice job of trying to address organic carbon versus carbonate carbon and whether this signal here is reflecting global records or if it's just reflecting differences in organic sources through time, because different organic materials carry with them different isotopic fingerprints. So this study was really helpful in looking at compound-specific isotopes to try and tease apart whether the bulk kerogen record was representative of global conditions or just changes in different sources of organic material. So by separating out different organic materials, you can then just compare, for example, pristane or phytane or any of these chains as what is the trend through time and how does that compare to the bulk? And what they found here was that in each of these systems, you still see a similar signal to the bulk trend. But this is one way to try and differentiate between different sources of organic material driving your shifts in carbon isotopes locally. Another thing you can do is look at material-specific isotopes. So similar to targeting specific fabrics for carbonates, you can do this in the form of looking at wood, for example. For this example, again, the Toarcian oceanic anoxic event, this negative isotope excursion, you can see this wood record pretty clearly follows the bulk carbonate record, and so is thought to be recording global signals as opposed to local signals. So if you use just one material, then you can try to get around some of these effects of different sources of organic material. Okay, so the last little piece to touch on here is chemostratigraphy. So this is a part that I haven't actually addressed yet. I've just talked about the caveats of carbonates versus organic matter, but now using this to compare one site to another and applying it to deep time and using it in models of CO2 and oxygen, it's really important to untangle local versus global signals in both of these records. And recently there was a review paper that talked through the best sampling strategy, kind of the resolution that's expected in section, and then considering stratigraphic completeness when you want to look at isotope curves and compare them. So here this paper addressed expanded versus condensed sections, where in some cases you'll have the same amount of time represented in much less sedimentation. And so you need to change your sampling strategy based on your sedimentation rates to keep it consistent. So here what they're showing is if you had a completed section with no hiatuses and no changes in sedimentation rate, this is what your sampling strategy should look like theoretically. And then here are 3 different situations or scenarios where you have changes in sedimentation rate, which dictates changes in sampling frequency, or should argue for changes in sampling frequency to keep things consistent. This paper also goes forward with pushing different sampling frequency and sample replicates for given horizons can change the resultant isotope curve, and as a result, your comparison and your correlation. So this is showing first datum for a biozone and the last datum for a biozone, and 3 different curves generated based off of variable sampling frequencies. So on curve C, you see consistent horizons being sampled and the running average through this. For curve B, you have variable sampling frequency, and then curve A, you kind of have the least sampling frequency, and then the resultant curves and correlations that could be misplaced or kind of hanging and not well established because of differences in sampling frequency. Another possibility, as I mentioned, that's shown in this paper, is variable analyses per horizon. So doing replicate analyses or multiple analyses per horizon will allow you to get a better sense for the isotope value of a given sample. And so this is, again, kind of the ideal situation where you have the most sample replicates for a given horizon and the running average that represents theoretically the true average of the sample. And then here, fewer replicates, but relatively similar signal. And then here in curve A, you have some points that are defined by just one sample analysis and others that are just two, and a very different isotope record relative to curve C. And if you have these different resolutions that you're comparing, there's a bunch of different correlation schemes if you're just matching one point to another. And so these are just kind of cautionary tales of things to consider. Another thing that's very important to consider when you're doing carbon isotope chemostratigraphy is stratigraphic completeness. And this is one of my favorite papers from João, who is a shale sedimentologist, and his paper that he has on understanding erosion and unconformities in mud and its effect on geochemical and paleobiological signals. And I think he wins for the best abstract of here for this is what the fine-grained sedimentary record really looks like. And what he notes in there is that you need to consider when you have hiatuses and when you have missing time in your record, that's going to affect your carbon isotope kind of morphology, what it looks like and how you compare it to other sections. So here, what he shows is a low resolution study that kind of picks on certain spots through time where you miss this punctuated shift through time that's represented by these hiatuses A, B, and C, whereas a high resolution study would be able to capture that potentially. And then here, if you expand that by accounting for how much time is missing from A, B, or C, how your isotope curve looks very different. And so it's really important to consider the stratigraphic completeness of a given section and how that's affecting the morphology of your record. And so again, kind of feeding back into this paper, this is also considered and showing that if you had an unconformity where you're, for example, losing a negative carbon isotope excursion, then it could look like you just kind of aren't having that excursion preserved there. And the same could be said for a positive excursion. And so with that in mind, I think best practices for utilizing carbon isotopes for chemostratigraphy, one of the main things is to be consistent with sampling frequency and resolution with the stratigraphic framework in mind. We have to always consider that while we are geochemists or whatever specialty you have, it's all through the lens of preservation bias in the form of sedimentology, and whether you have there's no such thing as a fully recorded record of time every single day, every single record in the rock record. So we have to account for the fact there's going to be gaps in missing time. Use independent time constraints wherever possible. So biostratigraphy or absolute age dates are ideal to be able to actually line things up with a different frame of reference, not just carbon isotopes. Bring in other geochemical and sedimentological tools to assess diagenesis and to try and tease apart these local versus global controls on your records. And this is kind of like a final point that I think is important of resisting correlating one-point excursions or wiggle matching, where you see kind of shifts through time. I mean, inevitably we're human beings and we see trends and patterns and we want to make comparisons and make lines between them, but it's really important to consider if that is actually truly representative or not, and if we're just kind of making it up with our what we're seeing. And so in summary, some of the main takeaways I think for interpreting carbon isotopes is you have to consider that every archive has its caveats. I think it's important to be upfront and do your due diligence to explain the local influence. I mentioned avoiding wiggle matching and circular reasoning by incorporating different independent time constraints wherever possible. Obviously, absolute age dates are ideal, but it's not realistic for every place. And biostratigraphy, again, is ideal, but not realistic. So trying to use these tools when available is really important. And again, where possible, trying to establish a baseline and recovery. I think this is also really important to get expanded temporal sampling. So it's not just an event horizon, but instead enough time beforehand to establish a baseline, and then enough time after an event to establish recovery so that you know what you're looking for. And ideally from geographically disparate localities. And this final bullet point here is just to work with experts across multiple specialties to interpret carbon isotopes from paleontology, sedimentology, inorganic, organic geochemistry, and then those with modeling perspective as well. So you can use the carbon isotopes to say something about changes in fluxes or burial rates utilizing carbon isotopes. And so that leaves outstanding questions in future directions. So first, I just want to address that I don't think that there's really a community consensus on what defines a carbon isotope excursion. We commonly use CIE and negative CIE and positive CIE, but we don't have a definition for what that actually means. Like how much offset is required to consider something an isotope excursion, and how does that change when you use different archives? So these are things that I think are outstanding questions that need to be addressed as community moving forward. And then 2 points that I didn't really have time to get into, but I think are really interesting future directions, are improving our understanding of diagenesis in carbonates. There's a lot of work on calcium isotopes and reconstructing, diagenesis using that lens, and also improving analytical techniques for organic archives. And I'm a little biased because I'm at Caltech and a lot of people in my group do this, but looking at not just compound specific isotopes, but position specific isotopes using different analytical tools like orbitraps on amino acids, which may not be realistic for deep time, but may allow you to track environment and physiological changes. And this is some work done at Caltech and Penn State right now, but likely other places in the future. And so with that, I want to stop talking and just acknowledge presentation materials and discussion from my PhD advisor, Ben Gill, Kayla, Michaela, Alex, and Ben Smith. And so with that, I will stop sharing, or I will I'll mute myself and take any questions. Thank you.
Great. Thank you so much, Selva. That was really wonderful.